Hey everybody, and welcome back to Calc 3 Online. So the plan for today is to start a new and very important unit. And it's the last chapter in this unit, or in this course. And it's basically where we put everything kind of together. So this is where we're going to take like everything we've really learned with vectors, vector valued functions, like all that chapter 2, 3 stuff, or 12, 13 stuff, sorry. And then we're going to meld it with all the integral work we did in chapter 15. And along the way, we'll also have to know about like partial derivatives and everything from chapter 14. So it's a very nice way to end the course where you're going to kind of have to make a bunch of connections between all sorts of different stuff. And so I'll kind of explain the main goal for the unit on actually the next slide, but the plan for today is just talk about one little part of this new unit, and it's something called vector fields. So vector fields are really functions, and they're functions where the input is basically a point, and then the output is a vector, like at that point, okay? So you could sort of take, you can take any of these pictures really, and it's like whatever coordinate point, I don't know, this is right here, there's some vector that's kind of pointing in that direction. And what you typically see is like, you sort of see this simplified version where they're going to draw all of them the same kind of magnitude, same length. Because like if you imagine drawing like, take this vector, it might actually be that long, but it gets really crowded with all the other ones. It's more of a, when you see these pictures of it, it's more of a way to kind of tell you like the general flow of things. Sometimes you kind of see a picture like this one where you can kind of tell that some of these vectors here are kind of a little longer, whereas like these are just more like dots, right? So sometimes they might try to show a little bit more of the arrow to kind of show, in this it's probably like current in the ocean, and they're trying to show that there's like a little more current here. So sometimes you'll get that, depending on the picture, like this one too doesn't have many vectors drawn, that you might see some where the magnitudes are a little longer, but don't always kind of trust the picture regarding the magnitude part, but you definitely can trust it regarding the directional part. So it just gets really kind of crowded if you try to draw the magnitudes all accurately. So a lot of times we kind of shorten things a little bit to make it work. But even here you can see that this might represent like wind or something like that. Just like this one would, I guess, kind of too. And you can kind of see like a bigger vector there, so it's like more windy. Sometimes they show that more with color, so you can see they're kind of trying to show, I don't know in this picture, like what the colors indicate, but I would guess that kind of yellow is the most windy spot for some reason there. So these things just show up literally all over the place, and I feel like all these are, these two are very directly connected. This one is just talking about, I think, current, but you can imagine this shows up in like a lot of physical sciences. Like if you study electricity and magnetism, you study vector fields all the time because you basically study the electric fields of different things. So they're literally just all over the place. Super important thing to make sure you understand. What we're going to study this year, or this unit, is really a bunch of different theorems. Okay, the unit is sort of split up into really important theorems. Anytime you ever see something that says fundamental theorem in math, you should definitely learn it because it's one of the most important kind of takeaways. So there's a lot to unpack here, to be honest, and probably when students talk about their Calc 3 experience, one of the first things that they kind of talk about is Green's theorem, Stokes' theorem, and divergence theorem. These three are like three of the really big ones. And, at a really simple level, what these things kind of do is basically what I have over here. You can use these theorems to help make us solve some types of integrals a lot easier, okay? Which is a super simple kind of idea, but it shows up in pretty complicated ways sometimes. So there's a lot to be said about all these things. But what we're basically, the main goal of this unit is we're going to literally work down it in this order. We're going to learn about, this one you already know about. Fundamental theorem of calculus. That's like, I would almost call it fundamental theorem of Calc 1. But this you already know about. So we got one of these down. But like the next section, 16.2, is all about something called line integrals. And line integrals are going to take a few days to really master. There's like a few different types of them and things like that. But then if you look in the text, 16.3 is all about this fundamental theorem of line integrals. And so this is kind of where we'll get started with these theorems, and then we'll learn about this thing, Green's and Stokes and divergence. You're going to learn about something called curl, which is like a vector operation, divergence too, and one thing you'll see sometimes is you're going to start to see like weird integral notation that you haven't seen before. So sometimes these theorems are written like that, or sometimes they're written like the way I had it with a little loop there. And same thing for any of these. This one, or it could have a little loop there. I personally like the loop way, okay? And I'll talk more about this, but this is what we call a contour integral, all right? And it's basically just something that you haven't learned about yet, but it's a line integral, which I will talk about, and I actually would rather use the word curve integral, but we'll talk. But it's a line integral over a closed curve, okay? But I'll say more about this eventually. And this thing is actually the same thing as this thing. And then this one is what we would call a closed surface integral. Okay, you're going to learn that this is basically one dimension higher from this thing, a line integral. Basically, you can either integrate this thing, a line integral problem, or this double integral. This is truly just like a double integral. And it's saying in Green's theorem that whichever way you want to do it, you're going to get the same result. And so think of it almost as like, in math, we have formulas for area, right? Like you could find the area of a rectangle with length times width or whatever. But you could also do like an integral problem. And there's like two ways to do that. And it turns out that like integral is like a more useful tool to do other things in math. Like not everything can be solved so nicely with area equals length times width. Think of it sort of that way. These are giving us ways to do problems that are much easier to solve if you know these theorems and stuff. So when we get to it, I'll explain a lot more of it, but basically the whole unit is just trying to get to a point where you can really understand this. And this is sort of built on this, and this is sort of built on this, and this is built on this, and I mean, even this you could argue is built on this. So these pictures will directly relate to it. One thing I do want you to see is like we're going up in dimension here, right? So, this is a dx integral. This is a one-dimensional kind of integral, so that's still going to be a one-dimensional thing that you'll see. And then this is, two-dimensional region. There's again going to be like a two-dimensional part going on here. It's a little bit different. And then this is a triple integral, so you're integrating over a three-dimensional sort of object. So you will see when we get there. But this is kind of the main goal for the unit. So I want to take a step back now, though, and like talk about these things called vector fields. So all of this unit will rely on understanding what a vector field is well. So this is the formal definition. So let D be a set in R2. And you got a vector field on R2 is a function f that assigns to each point x and y in that D a two-dimensional vector, right? So basically, no matter where you are, you can input a point, x, y, and you at that spot, you're like, this is the way the vector goes, this is the way the vector goes, that kind of thing. You can basically modify that definition to just fit any dimension you want. There's nothing wrong with saying that, like, at XYZ in space, you would have just like a three-dimensional vector, right, pointing in any of those directions. This right here is kind of the more like formal way that you're going to see it. And if you think back to like when we did a ton with vectors, the way that we denoted vectors was that we either put like an arrow on them or we did like bold like this. So typically you'll see the bold thing being used. So when you see a vector field, you're going to see this bold F, but you really can just think of that as like it's kind of a vector, right? It's like a bunch of vectors. And this is sort of the formal way that we describe them. So you're basically going to have like functions of x and y acting as the scalars for the I and j component if it's 2D. And so this could kind of sometimes be shorthand written that way. But this is how you'll see these things called scalar fields. So these are really just fancy name for these vector fields. And I'm going to show examples of them, literally right now. So I just want to actually like sketch a few just to kind of give you an idea of what we're doing here. So this one just says that no matter where you are, basically this vector field is defined by negative y, whatever point you're at, right? If you're at like 0, 2, let's just do that out. So 0, 2, it says it's going to look like negative y in the I component, so negative 2, and then x in the j component, so 0. So at 0, 2, so let me tick off some points here. At 0, 2, it's going to look like this. So 0, 1, 2, it's going to just point right about there. And you could do this like if you did, some more points here. Let's just do 0, 3 or something. You're going to get negative 3, 0, right? So up here, it's a little bit bigger, something like that, okay? If you did, let's do one that's like maybe at something a little more interesting. Let's do like f of 1, 1, right? Let's do like 1, 2. So 1, 2 would be negative 2, 1. Okay, so 1, 2, it's looking like negative 2, and then up 1, so it's kind of looking like that. Okay. Let's do one on the x-axis. You probably get the idea of this, but let's do like 1, 0. Whoops, comma 0. That's going to look like 0 and then 1. So at 1, 0, you get nothing in the x component, but then you get 1 in the y component, right? And so that sort of just keeps happening. If I don't know, I'll just do one more really quick. Let's do f of negative 2, negative 2. Let's do 1 over there in that quadrant. So here you're going to get 2, negative 2. So negative 2, negative 2. It's looking like 2 over, 2 down. So it's kind of looking like that. Okay. If you keep doing this out, you'll actually get basically like, you'll see some, kind of nice properties where any of the ones that start on the axes, either they're going to be like perpendicular to the axis. You're sort of getting a circular kind of pattern to all these vectors. That is kind of what they follow here. But that's basically how you sketch these things. They're not always super easy to sketch. You more just, I don't feel like I actually sketched them a lot in practice. I more just kind of conceptually can visualize what they do, because there's literally infinite amount of vectors, right? There's infinite amount of inputs, and you're going to get infinite amount of vectors out. So you can't sketch them all. What I end up doing a lot is stuff like this. So, and I'm okay with this too. So Math 3D has some awesome capabilities for vector fields, and I'll show some of this in class. It's kind of fun to look at, actually. But if you can have a 3D vector field, right? And it could be just defined this way. It could be defined as z and the k component. That's kind of what we think of there. So, at like, I don't know, even 0, 0, 1, it's just going to point 1 up. 0, 0, 2, it's going to be bigger going up. 0, 0, 3, it's going to be even bigger. So if you look at the picture here, you can kind of see that the vectors are like getting larger and larger and larger like that. And they kind of shoot off in two different directions, right? Because like down here, they're going to go bigger and bigger into the negative. And you're not going to ever get anything in the left or right kind of directions, right? Because you're not going to get anything, I guess, in the x or y is what the best way to say it, because it is just outputting vectors that have a k component like that. So everything else is 0, basically. Very, very, very physical things. This is an example of like a very possible vector field for a very famous physical property. And ones like this are like just too hard to draw. Like what they're trying to show is like it's stronger as you go in. And that's what I was saying before about how sometimes we'll like color things to make it look a little bit better. But in terms of like a physical property, this vector field, probably already thought of it, but it might represent gravity. So you could have like an object of mass there, and like there are these like forces that are moving sort of in on it could represent gravity. And like when you're further out, right, there's a weaker pull, but when you get really, really close into the sun or something, it's going to start sucking you in, or like a black hole does that and stuff like that. So this is like some sort of possible vector field for something like gravity. Not really going to make you sketch too many of these. I'm mostly going to ask that you can kind of look at some and interpret what they might be just based on these kind of scalar descriptions like this. Or maybe like do some mix and match and kind of, if I give you these and give you some pictures, be able to kind of see which ones would sort of relate. But I'm never going to really ask you to fully sketch out these. It's kind of a lot of work. One other thing that I just want to talk about in this video is something called a gradient vector field. So this brings up the memory of when we studied gradient descent. So I think I showed actually a vector field back then. I didn't really explain it or anything. But this is basically the definition. So these are fields which represent the slope change at a point, okay? They're just going to point in the direction of the gradient. They're very, very important for something related to conservative vector fields. Yeah, that is the right term. For a second, I thought it wasn't. And oddly enough, these fields conserve energy. And in a lot of physical things, it's kind of important to be able to identify what conserves energy or map where the energy loss is and those kind of things. It's like a very common question in a lot of problems, a lot of physical problems. And so this is like the formal definition of a gradient vector field. It's just a field where you're going to map out at every point that gradient, right? So you have the partial of f with respect to x and the I, f with respect to y and the j, and that kind of thing, right? Overlaying it, you can do things where you map like a function, okay? And then you could sort of analyze, like, the function could represent like some sort of maybe like trajectory of a flight or something like that. And the gradient could represent like, you can do all sorts of things where you could represent like the most wind resistance or something against your flight path. There's all sorts of different things here. They're just special vector fields that we will see a lot when we study this thing, these conservative vector fields. There's going to be a very important connection between this and that. So just as a quick reminder, because we haven't found gradients in a while, but to find a gradient vector, of this thing, you would just take the partial with respect to x. So we'd get this. And then we would have to take the partial with respect to y. So we get 2x squared y. And then, so what the vector field is basically the map of this gradient vector just at every given point. So those are your two like scalars that are kind of acting the way that I used them here. You know, here they were just minus y and x. But if you went through this kind of thing and just literally mapped out vectors based on that, you would be able to see this vector field. This is just a quick little reminder of so there's this thing called gradient descent where if you have one of these vector fields, you can kind of see how it could send you to like a maximum or a minimum. Because if you just, like if you were anywhere on the path, like here on the curve, and you just follow the gradient, so you just follow it'll basically send you like to the lowest sort of like point or the highest point, because it always moves in either, if you follow the gradient, I guess it goes uphill, right? And if you follow the negative gradient, it's going to take you downhill. But it represents like the steepest slope change if you follow the positive, or the steepest decrease if you follow the negative. So that thing there's going to be a lot more to come on that one. That's going to show back up in one of the later sections. But I just wanted to kind of show that special one in this video.